Thank you, Till, for the nice introduction. As you already said, my previous work within my master's thesis, which I'm going to present again next week at the ISPIS Geospatial Week, by the way, in any case, this work is quite similar. So I will later get also a little bit into in-painting and other approaches on how this could be used in the framework of urban digital twins. But I would like to start with this nice little image that many of you surely know. It's called Vision Boulevard Sonnenstraße. It was created by the city of Munich. And it is part of a project that aimed at increasing the amount of green spaces in the city of Munich, at improving friendliness towards pedestrians, and also improving climate resilience. And at the time, this digital twin was not intended to mirror reality, but to serve as a planning scenario that can be used for diverse applications such as simulations and many other things I'm sure you know better about than I do. The question that I want to tackle a little bit also with my work is, this looks nice, but how do we get to it? How can we actually create such a model that we can use for the many applications that these models have? And the answer, the state-of-the-art answer is quite simple. It's manual modeling at the moment most of the times. This is a pity because this comes with several limitations. And the first one is temporal limitations. Of course, it takes very long to do this. In this particular case, please correct me if I'm wrong, it took several weeks to model only this one 3D model. This is because in order to have it in a state where simulation can run on it, every single geometry has to be right and every semantic property has to be right. And as soon as there's a little mistake, the simulation software will crash and it won't work anymore. And in that case, it needs to go back to the modeler, it needs to be reworked, and this can take several iterations. With this, of course, come financial limitations because all of this costs money. People that model these things need to be paid for it. They take hours and they are educated, they have a certain expertise, so they cost a lot of money. And these requirements on expertise are quite large. So people need to be familiar with the modeling software. They need to be familiar with the standards such as CityGML, IFC. They need to be aware of certain regulations that are site-specific. For example, in Munich about the maximum allowed height of a building or such things. And all these things need to be taught and in the end, of course, paid for. Then there are also, as I already touched upon a little bit, I see now limitations in consistency. As soon as there is a single mistake, the model won't be able to be used for simulation directly, but it would need to be reworked. And then finally, there's limitations in objectivity. What I mean with that is that no matter how objective a person modeling tries to be, there will always be a personal influence of personal taste, personal experience, and so on and so forth, which for a community solution can be problematic. It doesn't have to be, but it could be potentially cause conflicts. But the biggest issue really that I see is the following, and that is that simulations and analysis can be really quick. They can be done within minutes, seconds, and for larger simulations, depending on the size of the site, it can maybe be hours or days. But they can render a model that was carefully created in lots and lots of work practically worthless within a few seconds. And then, of course, all these resources that would have been put into modeling could go to waste, because then a simulation shows that a particular scenario would not be worth investigating because certain effects are undesirable or are unacceptable for certain stakeholders. So overall, it would be nice to have a way to automatically generate planning scenarios in a quick and cheap way. And first, the good news, there is methods for that. So we have procedural generation, which applies certain architectural rules, for example, to create building models, such as in the work of Philip Bilecki with the Random 3D City engine. It's quite old, so there are very sophisticated procedural generation engines today. And there's also now AI-based work. For example, I would like to point out the work of my colleague from TUM, Changyu Du, who developed a framework, a multi-agent large language model that can produce entire BIM building models just from a verbal description. So one provides a description like I want a 7-story hexagonal building, and the LLM multi-agent will produce a correct IFC model of that within a few seconds. However, there are certain problems with these approaches. And the primary thing is that these are limited to purely greenfield scenario generations. So scenario generations where standalone scenarios are produced without considering existing surroundings into the generative process, which is of course crucial for urban planning because I mean, the Hamburg HafenCity might be an exception, but in most cases you will have some connections. So you have roads to connect to, you have other buildings that a new one would match to, and so on and so forth. So seamless integration is something that should be considered in scenario generation more often. And another problem is that many of these methods tend to underestimate the importance of semantic information that is necessary for diverse applications in simulations or analysis, and tend to purely produce geometric models, for example. That also often happens. So what we propose is to treat the concept of brownfield development as an in-painting task. May you raise your hand if you're familiar with the concept of in-painting, then I don't have to go. Okay, maybe I'll illustrate it again a little bit. So the idea is to fill in missing data in a designated region. So you can see the example here for an image, that the original image is masked with a binary in-painting mask indicating areas that should be replanned. And then a prompt describes the desired new content, which is then added to the certain region. And the idea is now to transfer this concept to the idea of urban planning. And I see I'm very, very short in time, so I'm going quite a little bit over my case study. For the case study, I decided to simply try it on OpenStreetMap data, where I aim to use a stable diffusion image in-painting model to replace regular junctions with roundabouts. That's quite simple, but it shows the concept. I used OpenStreetMap data as training data, and I evaluated the outcomes with some semantically meaningful metrics, namely radiometric properties, circularity, and the connectivity to roads to the newly instance. My methodology is quite simple. I have my OpenStreetMap images, I have randomly generated masks and semantic information from OpenStreetMap data that I incorporate into a training pipeline to train the stable diffusion model. I won't go into detail because of time issues. The results show a clear improvement in the results. So we have better connectivity. We have, at least in most cases, some halfway sensible output. But that's also the problem, that there are some things that corrupt the results, which are, for example, cartographic elements such as text or scene complexity. For simple junctions, it works quite well, but for more complicated cases, for instance, Autobahn intersections, the method still fails. For an outlook, in the future, I want to go from 2D to 3D, from 2D pixels to 3D voxels. That's something that we're working on currently, where we are curating a training data set, leveraging openly available LOD2 building models. And also I want to apply use the potential that large language models offer, primarily for quality control functionalities, but also maybe, as my colleague Chang Yidu very impressively demonstrated, to generate maybe also whole XML city GML buildings. That would be awesome. So with that, I would like to thank you for your attention, and now I'm open for questions.